Okay, let's now take a look at the 3 cases where we're going to apply the conservation of energy. So in the first case, we actually have a block whereby we're going to exert an external force to press it down. So the block is initially at rest, and we'll push the block down until the block is nearly fully submerged, and the block has been displaced downward by the distance d. Okay, so the work done by external force, which is actually your F external. So in this case, this work done by external force will be F times d, because d is the distance traveled in the direction of the force, plus actually the GPE loss of the wooden block, because in this case, the gravitational potential energy has actually decreased. These two, when added together, is the energy that's translated primarily to the energy stored, because the very moment if you release your external force, the block will actually be bouncing up. And that energy is because of the upthrust or the buoyant force that's pushing it up. Finally, the part that most often will be forgotten will be the fact that this amount of energy not only will be translated to the energy stored, it will also be translated to the GPE, the gravitational potential energy gain of the water, because the water level would have been risen. Certainly, we can assume that this value is small, provided the amount of water that you have is significantly larger than the volume displaced by the wooden block. In the next example that we actually have a M1G that is actually sitting on the a slope, and there will be frictional force, and it's now connected by a pulley, and this to a block M2G. So in these questions, the setting will be that M2, the mass of 2 is significantly larger than 1. So therefore, because of that, the motion will be such that M1 will be moving up the slope, M2 will be going down the slope. And of course, we are also assuming the frictional force, all right, between the pulley and rope is negligible. So with that, let us see how energy is actually being translated. As M1 move up and M2 move down, clearly M2 will be losing gravitational potential energy. And those energy will be translated to the gain in gravitational potential energy of M1. And also there will be the work done. Some of this energy will now be translated to work done against the frictional force, all right, acting on the block M1. The part that's typically forgotten is that this energy is now also being translated into the kinetic energy of M1G and your M2G. If we assume that the block M1 moved by the distance x upwards, M2 will now move downwards by the distance x as well. So in this case, the loss in gravitational potential energy of M2 will be M2 GX, while the gain in potential energy of M1 will be M1 GX sine theta, because this is actually the vertical distance that is actually being moved in terms of the block. Finally, the frictional force or the work done against frictional force will be Fr multiplied by X. And certainly we'll add in the gain in the kinetic energy of both block M1 and M2. So in the final example that we have somebody actually being secured to a bungee cord, and then he's leaping off. So there's actually 2 phases in terms of the energy translation. In the first phase, the man will be losing gravitational potential energy while gaining kinetic energy. This occurs when the rope is not being stretched or extended. The very moment when the rope is being stretched or extended, the loss in GPE actually will be equal to the gain in KE plus the gain in EPE. And you can see that at this point, when the speed is 0, then you will find that the KE in this case would actually be 0. So all the loss in gravitational potential energy is converted to gain in elastic potential energy.